All right, people, we are going to talk about the reduced row echelon form of A and what that gives us for our subspaces that we're interested in. We're very interested. I know you're very interested. It's very exciting. Okay, the plot thickens. It really does. It really gets quite deep here. So I've written out a few pieces here. We're going to have 4 kinds of reduced row echelon forms for A, and then we're also going to think about eventually reduced row echelon forms for A transpose. So just in words again, we're using elimination to take A, reduce, right? We introduce as many zeros as we can in a stair-step fashion now. We're not worried so much about just a straight diagonal. We find pivot variables, and they're the ones that we can remove everything around it in the same column. So they'll be just part of the identity matrix, 0, 0, 1, 0, 0, 0. And then there'll be free columns. And so we'll come back to this again and again. And we've started to see that how that connects to column space and null space, which we now know what those are as well. But we can make these kind of general statements about matrices based on their reduced row echelon form. All right, so let us get into this. So I'm going to say there are four basic kinds of R sub A. It's going to be very important that we have this R sub A. That's not always done, but that's a form we will use. Then what these R sub A's mean for AX equals B, your friend. So we've solved AX equals B with LU. That's what we tell computers to do. This is what we do to understand it more deeply, right? This next section about 4 subspaces, the big picture section. Keep going, people. Dig deep. All right. So if you have a stick, you might want to bite it. Okay. So, and as I said, the reduced row echelon form of the transpose of A, such a simple thing to do, just take a transpose, gives us everything else that we need. Now, just to be clear, we'll come back to this. You have to take the transpose, then do reduced row echelon formula, right? Then perform row reduction on that. You can't just take the transpose of the reduced row echelon form of A. We'll get to that. All right, these are the main things. Right, so the story so far, what we've learned so far is that R sub A, by definition, was what we said is going on with this thing, gives us the rank of A, which is, we'll write as small r, and that's the number of pivot columns. Right. Good, and then the null space, that comes out of solving AX equals 0, which through row reduction is the same as solving RA x equals 0. Right? Once again, the reduced row echelon form is different to A. We've destroyed the rows, but they have the same solutions, and that's why this method is what it is. We get to a much simpler matrix. It's very easy to solve. So there are 2 pieces, and then that tells us everything. That tells us the sort of the broad story of AX equals B, whether it has 0 solutions, infinitely many solutions, and more specifically whether those are, or 1 solution, and whether those are possible, right? Depending on what B is. So that's going to be these. It may not depend on B, but we're going to figure that out as well, right? All right. Okay. So again, just a little recapitulation. So 1 and 2, these points 1 and 2 about the rank of R and the null space, they dictate some behavior for X, the behavior of AX equals B with respect to its solutions. All right, so we saw this. So if 1 or more rows of the reduced row echelon form is 0, then it's possible, we can always construct that there's a B such that when you do its row reduction, there's a non-zero value here, right? So all zeros, so 0 equals something non-zero, so it won't work. So there are no solutions. So if the rank is less than m, right, the number, so it's going from columns to rows. So if the number of, and we'll have pictures in a second, but the number of columns that are pivot columns, that's R, if that is less than the number of rows, then that means we will have a row of zeros or 1 or more row of zeros, which means it's possible to have no solution. All right, so that's what that dictates. It's possible to have no solution. We could have 1 or infinitely many, but it depends now on B. If the rank is equal to m, then it doesn't matter what B is. We'll always have a solution, which is to say, well, we'll get to it, but the column space fills R sub M. It's the same as. Now, the null space, there's always 0, right? A times 0 is always equal to 0. So 0 always is there for the null space. The question is whether there's more, right? Is it a one-dimensional thing, two-dimensional thing, three-dimensional thing inside of Rn, the number of columns? And it depends entirely on whether Ra has free columns, right? So the pivot columns are the identity pieces, and then everything else is a free column. And if there are free columns, that means when we solve the problem, we express the pivots in terms of the free. We're going to do this many, many times. Pivots in terms of the free, and the free can be whatever they want, right? So what we'll see is and then we have infinitely many solutions, right? So if B is in the column space, and I'm going to add that here. So which is if B is in the column space of A. Right, so if B is in the column space of A, it means there's a solution. The columns can be combined to give B. Then if the null space is not equal to 0, there are infinitely many solutions. Okay, great. Great. Let me remove the yellow bits. Okay, so let's have 4 examples, and perhaps you want to go back to the start of this again and then refresh, and then we'll have a table. So sort of the end pieces will be good things to return to. So let's say we have this. So this is, I'll call it 1, a little thing like this. So R sub A, just an example, equals 1, and these apples are going to be different things, all right? So we'll say this is 1, 2, this is apple, let's make this bigger, 1, 3, 0, 0, 0, right, like this, 1, and I'm making one where, right, let's maybe we have this. This is another identity piece, 0, 0, this is an apple, so this is 1, 5, that's a 3 there. Okay, so I'm just setting one up. This is just an example, 2, 5, and 0. We've started with some A, we've done all this row reduction. So let's look at this, what's the anatomy of this thing? Okay, so here's our stair step, all the way across here. Important thing to write down, just as we've always from the start said how important it is to write down just the shape of the thing. So this is M equals 3 rows, N equals 6 columns, and then how many pivots? And then that's the rank, 3. So let's indicate that. So this is pivot, and then free, and then I'll just write free pivot, free pivot. Okay, so there's always a solution to this. So this is a case where there's always a solution. So this is what we know so far, right? So we see there's always a solution to the original thing, equivalently to R sub A, solution to A x equals B. Because there's no, right, so no row of zeros. No row of zeros. And this is this M equals 3 case. What's going on here is that these, M equals 3 equals the rank. These things are the same, right? So there are 3 columns. Let's draw this, yeah. 3 columns, boom, boom, that are pivot columns. And think about how that works. So that means that as you go through each column, you're going to have 1, 2, 3. They're going to step down with the pivot entry being in the first row, the second row, third row. So you could put them together, make a square matrix, and that means that the number of pivots will be the number of rows that are non-zero. Right. So if that is equal to the overall, I'll leave it like that. If that is equal to the number of overall rows, then there's no way you can have a row full of zeros. You always have a solution And in this case, it means, and we're going to get to this, it means that R, let's write it like this, the column space of A is equal to R3, which in this case is equal to Rm, which is equal to Rn, R to this little r. Right, they're three-dimensional. The most it could be is three-dimensional, right? These are three-dimensional vectors. If you look at this, there's 6 three-dimensional vectors. We're trying to combine them to make another three-dimensional vector. So that should start to make sense, right? We've got lots of columns. They could all be the same, which means that, you know, you can't make much out of it. But if they're all different and they're pointing in different directions, then there's a pretty good possibility that we've got a lot of, we can cover all of 3 dimensions. Right. More of this will settle in. You must grit your teeth. And in this case, null space, how many free variables? So that's part one. Also, the null space of A is three-dimensional. Is a 3D subspace of R6. Right, and this is n equals 6. Right, the x is a 6-dimensional vector, right? X's live here. X is 6D, is a 6-dimensional vector, right? Or let me say x lives in R6. All right, that's good. That's good. But we know the null space is three-dimensional. It has, we'll get there, right? We have to prove this, right? We have to prove this. This is to be proved. Proven, shall we say, past tenses. But the idea is there are 3 free variables, so it's starting to look okay. But we know it's certainly not 0, right? But we know the null space is not equal to 0 because there are free variables. We'll get a nice juicy solution. All right, so that's, and so the upshot for this one, so these are things that we can see, and then the upshot, or so, in this case, Ax equals b always has a solution. Has a solution, and there are always infinitely many. And we're seeing the reasons for these pieces, right? So this is to do with null space, and this is to do with column space. Can you do it? Can you do it more than one way? All right. Good. So I'm going to call that 1. Let's maybe jump to the next page. So this is going to be 2. So imagine, so that was a rectangle, that was a wide, right? This is a wide shape, a wide A, from a wide A, right? Okay. Good. Which is an important, right? The overall shape of the matrix. It controls for what's possible to some extent. So the rank is the big deal inside M and N. Yeah, and that's what I should say. So everything, yeah, N, M, N, and the rank will give us everything we want in terms of sort of the basic story. So let's have another one. This is RA. Let's imagine it is a case where it's square and we do our row reduction, we get the identity. Equals the identity matrix. So this is M equals N equals R equals 3. Right? No free variables. If we look at these columns, they are all, right, pivot, pivot, pivot. Okay, so we've reduced a nice, so it's got 3 pivots, that are not, right, they're all good. And in this case, it doesn't matter what b is, right? So b, so we see in this case that ax equals b is always solvable. It's the same story as before. And then there's no, that null space is just 0, no free variables. So, and there are two things, the null space of A is just equal to 0. So those two things together, right, so no free variables. So there's no way we can't add, once we've got a solution, we can't add, we can't play around with it and add some null vector to it, which allows us to, which is how we get to infinitely many from our previous work, right? So, and we're going to come back to it, come back to it, come back to it. Good? So, in this case, I'll try to use the same thing. So very important thing here, ax equals b always has one solution. Has one unique solution. That's it. Always has a solution, and there's always just one. And another thing to see here is that for square matrices, for square invertible matrices, ones we can undo. And now we're talking about n by n, arbitrary. So I'm just going to say this. The reduced row echelon form of such a thing is just the identity always, because right, it sends each x to a b and we can undo it. If there are multiple x's that go to the same b, and in principle will be infinitely many, then there's no way we can undo that, right? So and this is the story, if A has a non-trivial null space, there are some x's that go to 0 and you can't undo that. You can't go to 0 and say, oh, all of these different vectors came from it, because it's not a one-to-one mapping. It's a many-to-one. Okay. So this is a one-to-one mapping from, it's a delicious thing, and I know the excitement is palpable, but just, take it easy. Okay, so 3. Let's imagine we have one that's tall, right? So we'll have a tall one, and these are just examples, right? So 1, 0, 0. Make sure we've got all our pivots here. So if it's tall, this is possible. And in this case, we've got m equals r equals 3 and n equals 4. Okay, let's get this right. M is equal to 4 and n equals r equals 3. So this is a tall matrix, and it's filled out in terms of pivots across. Now, there's no way it can make, right? Because it's tall, it's actually, it will always have a row of zeros. Tall matrices will always have a row of zeros. So tall matrices must always have a row of zeros, which means it's possible to have no solution. Have a row of zeros, right? One or more, depending on the size and so on. So this is things we have here. There are no free variables, but it's possible there's no solution. So no free variables means there's no null space. Null space equals equals 0. Okay, so these things, so we have this, we see this, and plus possible no solutions. This is equal to 0. So therefore, ax equals b has 0, or one solution. It depends on B. It has one solution if B is in the column space of A, and 0 solutions if B is not in the column space of A. So again, the null space controls whether there are infinitely many solutions, if there is a solution, or 1. Null space equals 0, there can only be one solution. Null space is not 0, then there can be infinitely many. And then the column space, if B is in the column space, that controls whether or not there's a solution at all. Okay, so 2 different things. Let me go back and annotate this one. So I should, maybe I'll just add it down here. So note wide A's always have at least one free variable. So they always have a null space that's non-trivial, always have at least one free variable. Let's get it done. Which means null space of A is not equal to the, you can always just say it straight away, wide null space of A is not equal to 0. And in this case, you can always say it's possible there's no solution for the tall version. All right, so there's a fourth possibility, which is that, and it could be, let me get my Roman numerals right. So it could be a square matrix, doesn't matter, but we have M and N are greater than R. So example might be, yeah, so similar to what we've had, right? So 1, 0, 0, maybe there's a apple here, 0, and then a 1, something like this. It's a bit like our friend Fezzik. So let's make that a 1, 2, and a 1, 4, and a 2, 4. So pivots, excuse me, pivots, free, pivots, free. Right, 2 pivots, 2 free. So in this case, we have, for just this example, it's just an example, we have M equals 3, N equals 4, and R equals 2. So this is a case where this is a 3 by 4 matrix, but it's really kind of a 2 by 2 matrix. That's really what's happening. So later, this is really a 2 by 2 matrix, right? 2 by 2 matrix hiding in a 3 by 4 matrix. So what does that mean? It means that it's actually, it takes a plane in 4 dimensions and maps it to a plane in 3 dimensions. And it likes those planes, and everything else it can't handle, it sends them to 0. Right? So it sends, so A sends a plane in 2 by 2 in R4 to a plane in R3. And that's invertible. It's, if they were the only things we knew about, this plane and this plane, matrix A does that. That's a big deal. That's a big deal. All right, so let me put in these pieces, the echelon pieces. They're here, and this one is boom, 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 boom. So it's possible now, because there is a null space, so we see these things, so we see the null space of A is not equal to 0. It's not just the 0 piece. Free variables exist. The column space of A or may or may not contain B, right? And the reasons for these, I'll just put them here. This is because 2 free variables, and this is a row of zeros. It's that little f, row of zeros in R sub A. Yep. Okay, so it's possible. So the second one says possible there may be a solution or not, And if there is, there will be infinitely many. So in this case, we have either 0 or infinitely many solutions. Right, so far we've had these things. So there's one unique solution here. There are 0 or infinitely many solutions here. There's either 0 or 1 solution here. And back here, the first one we had, there's always a solution, and there are infinitely many of them. So I'm going to put that together in a little graph here, which we're going to add to a chart, and we're going to add to as we go along. So this is a case where, yeah, okay, do it like that. Yeah, that's good. We clean out some bugs here. So this should be, I want that to be an equal sign. So we get this right. So m equals r and n equals r. So these are all the same. So this is square. M equals r and n is greater than r. This is a wide example. And this is a tall example. M is greater than r. And this is a case where we're not sure, right? So it could be many possibilities. Right, so the examples might be, so this is just as we had it, the identity matrix, so 3 by 3. So we'll try to do 3. So the number of solutions here is 1, always. M equals r and n is greater than r, so m is columns, n is this, right? So this is, I'll give you one, it doesn't have apples. 1, minus 2, 0, 0, 0. And then 1, say, minus 3, minus 4. This one. All right, here's our structure. So it's going to be pivot, free, pivot, free, pivot. And just look at this again, right? We've got the identity matrix here. There's nothing, right? We could use this minus 3 to get rid of this minus 4, but it would mess everything else up. So that's the story, right? We can only do as well as making the pivots into, the pivot columns into the identity matrix structure. So this one always has a solution, and there are always infinitely many. Right? The null space is not infinitely many solutions, always. And I'll add a little, let me add a little annotation here. So the column space of A is equal to Rm here. The null space of A is equal to 0. In this case, the column space of A is equal to Rm again. And the null space of A is not equal to 0. It's not equal to the 0. It's not very good. So those things. So we're nearly finished our little example here. So a tall one, just as we had before. And this is a case where n equals r. So there are pivot columns, right? They're all pivot columns in this case, just as in this first example, all pivot, but it's a tall matrix. And because of that, everything it will look like the identity with zeros underneath. Right, there are no free columns, so everything can be cleaned out except for the pivot variable entries. So in that case, we have there's no null space other than 0, right? It's no non-trivial null space. So it depends on B. It's the row of zeros is the issue here. So there will be 0 or 1. And we know the null space of A is equal to 0. That's why there aren't infinitely many. and here's the column space of A. This is not equal to Rm. It doesn't fill it up. Now the last one will be 0 or infinitely many. Number of solutions. Guess I should do that. And in this case, we have the column space of A, again, not equal to Rm, and the null space of A is not equal to 0. Yeah, so here's the last piece, last example. We've just had some, so 1, and I'm just going to put in some numbers again. -2, 0, 1, and then let's say -7 and 12. 0, 0, 0, 0, 0. So there's a row of zeros and not enough pivots. Okay, so this is right. There's a much deeper story now. Super exciting. What we have to show is, you can kind of start to see this, and I've said it before, the dimensions of these subspaces, right? So two-dimensional subspace inside a three-dimensional, whatever it is, we want to tie it to rank. So this is going to be a very nice thing. So the next piece will be, so this is next, I'll put it down here, next. We want to do this, we want to find a bases, right? So how do we describe these subspaces? So we're going to find bases for subspaces, and so which will mean column space of A, and then null space of A for us. And we're going to see, so that's one thing, and we're going to see the dimension of the null space of A, or the column space of A first, is equal to R, and the dimension of the null space of A is equal to n minus R. Right, and those things will just stick out and tell us what's going on, right? If your dimension of your null space is not 0, then there's some stuff in it, and there can be infinitely many solutions. And if your dimension of your column space is less than m, which is where your vectors are ending up, when you A times X, B lives in Rm. If you can't make everything there, then it's possible there are 0 solutions. All right, things are getting tougher. Concentrate.